Hello, everyone, and thank you for joining this NannoTalk. My name is Boris KARATSOLIS, and I'm a calcareous nanofossil micropaleontologist and paleoclimatologist. I completed my bachelor and master's degree at the National and Kapodistrian University of Athens in Greece, my PhD at Uppsala University in Sweden, and I am currently a Utopia SIF Marie Curie postdoctoral fellow at Vrije Universiteit Brussels in Belgium. Throughout the years, I have worked with living and fossilized calcareous nanoplankton from multiple ocean basins, including the Black Sea, basins within the Mediterranean, the North and the South Atlantic, as well as the Eastern Indian Ocean. Today, I will be talking to you about the work I conducted during my PhD, which focused on the Northwestern Australian Shelf. This area is located within the dynamic climate system of the Indo-Pacific Whirlpool, where modern ocean circulation is controlled by the warm water brought to the Indian Ocean by the Indonesian through flow and further transported southwards by a major southward flowing boundary current named the Leuven current. In the paper that I will be presenting to you, me and my PhD supervisor, Jorantje Hendricks, studied the late Miocene to Pliocene sediments recovered from sites U1463 and U1464. Both sites were drilled during the International Ocean Discovery Program Expedition 356 and are marked in green. Two astronomically tuned calcareous nanofossil time series were investigated, and they identified shifts in the assemblage of dominant species were compared to paleotemperature reconstructions from the area. A key for the investigation was the construction of a nanofossil stratification index as a ratio of the relative abundance of species indicative of more oligotrophic, stratified conditions in the water column, divided by these species plus species indicative of a well-mixed water column and more eutrophic conditions. The higher the index, the more stratified and nutrient-limited conditions prevailed in the upper water column. Another important aspect was the calculation of the Shannon Diversity Index. A decrease in nanofossil stratification index is observed between 5.4 and 5.2 million years, as you can see in panel A, and an increase in nanofossil diversity is observed between 4.6 and 4.4 million years, as you can see in panel B. In this figure, you can see a summary of the main results of this study, combined with paleotemperature records from the area and other important paleoclimatic and calcareous nanofossil evolutionary events for the study period. In panel A, we observed a decrease in nanofossil stratification index that we talked about and occurred between 5.4 and 5.2 million years and coincides with a decrease in upper water column paleotemperature at site U1461, which is located on the edge of the Northwestern Australian Shelf. In panel B, we see how the observed change in nanofossil stratification index coincides with a warming in sea surface temperature at ODP site 763, which is located further offshore, but still within the path of the Leuven current. What we proposed in our study is that the combined observations of the nanofossil stratification index and the paleotemperature reconstructions indicate that the Northwestern Australian Shelf transitioned from a period of more stratified tropical conditions before 5.4 million years to a dynamic shelf environment with seasonally increased water column mixing after 5.2 million years. We attribute this change to intensified activity of the Leuven current, which in modern environments flows seasonally and mixes the water column at the shallower parts of the Northwestern Australian Shelf, decreasing temperature and increasing nutrient availability, while at the same time it transports the warm water, which can be recorded to increase the temperature further offshore. In panel C, we show the broad-scale change in low-latitude paleoproductivity that has been documented between 4.6 and 4.4 million years. And although it led to the restructuring of the nanofossil assemblage and an increase in diversity, in nanofossil diversity in our sites, it did not influence the nanofossil stratification index. What we learn from such a study is how we can use the ecological affinities of nannofossil species to infer and understand changes in ocean circulation and current intensity, as well as seasonality and stratification of the water column. We also showed how important it is to compare observations from different sites that belong to other systems and sedimentary regimes, and how we can decouple more regional signals from both broad-scale patterns in paleoproductivity when studying calcareous nanofossils. At the same time, we were able to add information to the history of a major boundary current during a key warm period of Earth's history and across the important geological transition from the Miocene to the Pliocene. Future research can help us further investigate the climatic drivers behind the Leeuwin current intensification that we observe, as well as late Miocene and Pliocene calcareous nanofossil paleoecology and paleoproductivity across different bases and latitudes. More astronomically tuned records are key if we want to explore the synchronicity of events that impacted calcareous nanoplankton evolution and ecology, as well as the paleoclimatic and paleoceanographic processes that led to them. Thank you very much for your interest in our research, and please follow the links to check our complete study, which was published in Climate of the Past.